Well, here is our code, and this code was already explained in the last class. Then I'm going to explain the new functionality for the time. In this case, we define, first of all, we define a method. In this method, we set two variables from the file config.json and return these two variables. Then create, we define other method, and in this method we get an interval in the arguments, and we create an infinite loop. We use the previous method to set two variables and update this method every 1 second in this case. Then we initialize the variables, we create a thread, we pass the previous method, and this thread is created in order to execute this method every 1 second, and then we initialize the thread. And in here we put the two variables. Well, in here I'm going to show you the functionality of the application. And here we have the application. We start application, and we can see that we have already defined two variables, and we change these two variables from the configuration file. Here we can see that we have new two variables or new two values for these variables.
Hello, in this part of the video, I'm going to explain the sequence diagram about the perf command. Start with elements of the diagram. We have H1 and H4. These are the hosts or endpoints participating in the performance test. We have S1, S2, and S3. These switches facilitate package routing within the network. And finally, we have C0. This is a central controller in a SDN environment managing routing logic and policies. These these are initial TCP messages. We have TCP segment sign. Sign segments are part of the TCP three-way handshake, initiating the connection establishment between H1 and H4. There are also packet in and packet out. Packet in indicates that a switch has forwarded the package to the controller to the absence of a pre-existing role to handle this new traffic flow. And packet out when the controller responds with instructions on how to handle the packet. Generally, configuring the switches to allow future packets from this session to pass though. uh, the connection establishment process. And so the TCP segment sign is sent from H1, though the switches S1, S2, and S3 to H4, signaling an attempt to establish a connection. The involved switches send these segments to the controller C0. Uh, this is packet in to obtain guidance on how to proceed. The controller C0 evaluates the request and sends the routing decision back to the switches. And this is packet out, enabling the proper processing of sign and acknowledge segments. Uh, the part of exchange of TCP segment acknowledge segments are sent in response to sign segments synchronized as part of three-way handshake, facilitating the confirmation of the connections. Finally, we have other TCP segments. This indicates the continuation of the TCP packet transmissions that will be part of the hyper performance test, including the test data transmission once the connection is established. This diagram specifically shows how the initial connection establishment for an hyperv command is handled in a SDN.
In here we can see the sequence diagram. When the block operation is enabled, we can see that the host 1 is trying to communicate with TCP protocol. The host 1 send a TCP segment to the switch 2, and this one try to send a packet in to the controller in order to get some information about how to manage the packet, but it doesn't work. And that is the reason because the host one tried to send again a TCP segment, but it gets the same result. Well, I'm going to explain the deployment map. The deployment map shows us how from a Windows server we are creating three virtual machines through the VirtualBox software. In this case, we have the Ubuntu virtual machine, the Mininet virtual machine, and the Rio virtual machine. The Mininet virtual machine and the Rio virtual machine are connected through SSH connection to Ubuntu in order to create a network in which we are running the forwarding plane in Mininet and the control plane and application plane in Rio.
In the image, we have the architecture of the network for this application. To start with, application plane that contains that application that interact with the SDN controller. In the diagram, we have two files, tigertcp.py and ora.py. This Python script contains the logic to block TCP protocol traffic during specific blocking times. It interacts with the radio controller to dynamically apply these TCP blocking rules to the network according to the schedule defined. And ora.json serves as a configurable schedule that can be modified to specify the times when the TCP blocking should be active. Changes to this file allow for easy and flexible adjustments to the blocking schedule without needing to alter the core application code in tier TCP.py. The northbound interface in this case is the API Python that enables the communication between the application and the SDN controller. It allows the application plane to program the network dynamically using a high-level programming language, in this case Python. The control plane, we have radio controller, which has an IP address in the image. Radio controller is responsible for the overall management of the network, making decisions about where and how data packets should flow through the network. It communicates with the switches using the southbound interface. Southbound interface uh, is OpenFlow 1.3 that serves as the communication protocol between the control plane and the forwarding plane. OpenFlow allows the radio controller to interact directly with the log tables of the network switches. In the forwarding plane, we have Mininet with the IP address in the image with different open virtual switches and hosts. These switches handle the movement of packets across the network based on the roles and policies defined in the tier TCP.py. Each switch connects to various network nodes or other switches.